Okay, so this lesson is 2.1 Quadratic Transformations Part 1, and the objective will be to graph quadratic functions using transformations from the parent function. Okay, now I forgot to write that in there, but I'll make sure to include it in the assignment. Okay, now the parent function, which is listed right here on the right, is the simplest function in a family of functions. And what we mean by that, it is the absolute most basic way to represent that function. So here for quadratic, the most basic way to represent that is with x to the power of 2. You cannot have anything more simple than this be a quadratic function. Just like the parent function for a linear function would just be x. Okay, nothing more simple than that. Now, a quadratic function, listed over here on the right, is an algebraic function to the second degree. It reveals a U-shaped pattern often called a parabola. And you probably are familiar with that. That's that U shape. And that U can look very different. It can be close together, far apart, upside down, but it cannot be left and right. And what I mean by that is it cannot look like this. Those are not quadratic functions. They just look like it. Okay. Now when we say the second degree, that just means x to the power of 2. Okay. Degree is another way of saying what's the highest power. Okay. All right. So now that we got that terminology out of the way, let's look at what the most basic quadratic function looks like. So I'm going to take these values, -2 to 2, and plug it in. So if I take -2, I go to x, that's -2 squared, that becomes 4. Okay. Then I do it with -1. -1 squared becomes 1. And that's because it's -2 times -2, right? -1 times -1. Then we have 0 squared is 0, 1 squared is 1, 2 squared is 4. Notice this pattern, okay? When you plugged in a negative number and its positive equivalent, okay, you got the same answer. So I plugged in a -2 and a +2 and I both got 4, right? I plugged in a 1 and a -1 and I both got 1, okay? And then down to 0, 0, which has no equivalent on the other side because that would be what's called the vertex, which we'll go over a little bit more on the next page. So when I go to plot this, I have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And then I should get something like this. Okay, this is the absolute most basic quadratic we could have, okay? And we also need to focus on the domain and range. So for the domain and range, just like we've done in the past, right? We see that this is going forever to the left. It's going forever to the right. So its domain is all real numbers. And then its range is kind of cut off here. If we notice it, it's the lowest value we see is 0, right? So y is greater than or equal to 0, okay? So all of this should feel pretty familiar. All right, but I want to get into transformations, okay? Now, these two words seem kind of tricky to people, right? We have transformations and we have translation, okay? Transformation is a change to the position, size, or shape of a figure graph. Basically, it's anything we do to adjust it. Change its position, up, down, left, right, okay? Move it up, move it down, move it to the left, move it to the right. Its size. Is it close together? Is it far apart? And that also kind of falls on into the shape, right? We can stretch that U to be really wide. It could be really close together. Now, a translation, notice how it includes the word transformation in it. A translation is a type of transformation, okay? And that moves the figure and graph's position without altering its size or orientation. So what we mean by translation is we mean up or down. We mean left and right, but its actual graph would not look any different. The parabola, the U shape, would be exactly the same. It would just be in a different location, okay? So translation is more limited than transformation. Transformation covers all the things we can do to it, okay? Now the next thing we have is a vertex form listed here, okay? The vertex form is going to be the formula that we use to easily graph these quadratic functions using transformations. Okay, now that was a mouthful. That was a lot of stuff there. Okay, Think of it this way. For linear functions, you have y equals mx plus b, right? And we know when it's written that way, we have a slope, we have a y-intercept, and we can assume those things because it's written this way. This is like a form for the quadratic. When it's written this way, we can assume certain things about it, okay? For starters, we can assume that this minus h is going to be our horizontal translation. Okay? And then our plus k is going to be the vertical translation. Now notice how it's a plus k and a minus h. Okay, this is going to change some things here. It's going to kind of flip the value that we would see. So if we see a plus 3, if we were to see like an x plus 3, well, in order for that minus h to have gone to a plus 3, it would have meant that h is a negative, so that you got a negative to get a positive. So we're going to go over that, but I'm just warning you right now, this is a big point of confusion for people, is the minus h. Okay. Now a does something very different to this graph. Okay. This is going to stretch or compress the graph. Now, stretch and compression we're going to leave out of this lesson, and we're going to leave it out because we want to just focus on the translation. So we are just going to be moving it left and right and up and down. Now, before we go on to do that, if you notice here it says transformations with Desmos, I just want to do a quick investigation of what these transformations look like using Desmos. So right now in Desmos, I have the parent function graph. So you can see in the top left, I have our formula, our vertex form, a times x minus h squared plus k, and then I have 3 sliders, one for a, h, and k. A is set to 1, h is 0, k is 0, which means that this is our parent function, okay? Now, and think about that, right? If h is 0 and k is 0, it just means that there's x squared, a is 1, 1 times x squared is just back to x squared, okay? Watch what happens when I change the h value to positive 3. See how it moved to the right? But think about this for a second. That's an x minus h. So when I write my formula, that would be x minus 3. So we're going to see the opposite there. Now when I move my slider to the left to negative 3, we see it move to the left, okay? But think about it again. If I plug in negative 3 in for h, that's a minus negative 3. It would turn to a plus 3. So whatever you see for the h value is going to be the opposite rotation, okay? When you actually see it as a formula. Now for k, look, I go up, it goes up, I go down, it goes down. It's a very simple translation, okay? And because it's a plus k, whatever number you're going to see there is what you get, okay? And now for a, which we're not really going to cover here, you're going to see the stretch and compression, okay? And even flipping it, okay? We see a lot of interesting behavior with the changing of a, but because it does so many different things, we're going to put that one to the next lesson. So h moves it left and right, right and left, and k moves it up and down. All right, but notice how the graph is still the same graph. So if I zoom out here, the shape of it, even if I'm moving it up, well, that's weird, doesn't change, okay? Only a changes the shape. You see that? Now we're almost ready to move on. This is the last thing I want to talk about. Vertex form. We have to think about that name. It's called the vertex form because we can see the vertex, just like slope-intercept form is called that because we can see the slope and the y-intercept in the equation without doing any manipulations. It's the same thing here. We are able to see the vertex. And that vertex is going to be the h and k value. Now, what is the vertex? The vertex was that point that didn't have an opposite. So in the parent function, in fact, let me just go back and look at it. The parent function, this point right here, is the vertex. It was 0, 0. It did not have an opposite point on the other side. It's a single point, and it ends up being the highest or the lowest point. Now let's start doing some graphing by transformations, okay? The first thing you want to do is identify your h and your k values because those help you find your vertex. So here, you have to remember the opposite. I know we see that this is h, but it's supposed to be written like this, x minus h. So in order for it to become a plus 3, h would have had to have been a negative 3. So that when you plug it in, minus turns to a positive. Now we don't see a k, so that must mean it's 0. So our vertex is negative 3, 0. And we'll get to domain and range, okay? What you can do with this without having to go and do a table, because we could just do a table again, but think about this. Where's our well, we know where our vertex is, but we can't just plug in negative 2, negative 1, 0, 1, and 2 all the time, right? So if we move it from the parent function, it's pretty easy to graph, okay? So look at this. This was our parent function, 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Look, horizontally shift 3 to the left because it's a minus 3. So all of these points would go over to the left, 3, and then a vertical shift of 0, so we don't even go up. So I can move all these over 3. So look, 3, 3, 3, 3, 3. Look at this. That's all I did, was like that, okay? Now that might seem confusing for a lot of people, okay? Why did we shift these points? Why couldn't we have done it a different way? There are many different ways, but sometimes it could be kind of tricky to find out what points to plug in when it's not in the center anymore, all right? And then knowing the parent function is also really important. Okay, and so that would be our function. Now our domain and range is pretty similar again, right? It's going forever to the left, forever to the right, all real numbers. And then you have your range. Y is greater than or equal to 0. Now let's do another one, okay? I'm going to go a little bit quicker this time, all right? We find our h and k. It's a negative 1, so pick the opposite, plus 1. For k, what you see is what you get, negative 4. Our vertex must then be plus 1, negative 4, okay? Now I'm going to put in my parent function. And, because it is the most simplest one, it's pretty easy for me to remember that, right? It's 0, 0, then it goes to 1, 1, and then 2, 4. And then it's just the opposite for the other points, okay? That means this one shifted 1 to the right, down 4. So this one went 1 to the right, down 4 spaces. And so it would be here, okay? Now let me erase all that, okay? So 1 to the right, down 4, okay? 1 to the right, down 4, 1 to the right, down 4, 1 to the right, down 4. In fact, let me just put these as points instead of x's. And then 1 to the right, down 4. And that would be your function. Okay. Now the domain is still the same on this one. And I hope you're kind of seeing the hint here that for quadratic functions, you pretty much always have all real numbers as your domain, unless it's cut off somewhere, all right? Because it's always going for, infinitely to the left, infinitely to the right, but your range has changed, right? It's gone down to negative 4, it's going up, so y is greater than or equal to negative 4. Now here's your next one, okay? Now this is a you do. I want you guys to pause and try this one. Find your h and k, find your vertex, shift it from the parent function, and then tell me what the domain and range is. Okay, hopefully you've given that a try. The h is negative 2, it's opposite. The k is 1. The vertex is negative 2, 1. I just put those together. And I'm just going to shift from the parent function. Okay, so that's 2 to the left, and that's 1 up. Okay, so 2 to the left, I'm going to move my vertex 1 up. Here's my vertex. 2 to the left, 1 up. 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 All I did was shift each point, like so. Okay. All right, domain and range. We got all real numbers again. Okay. And then our range is y is greater than or equal to 1. Because we can see it does not go below 1. Now I'm going to talk a little bit more about these shifts. Okay, and I think maybe I could have done a better job of explaining them. If you have a negative h, it's going to the left. So negative goes to the left, positive goes to the right. If you have a positive k, it goes up. If you have a negative k, it goes down. All right. Now the last thing you're going to have to do is describe the transformations given the vertex form already. And notice how the a values have been left out of these. Also, we're going to be doing those in the next lesson. So here we would say that this is a minus 9, right? So we flip that, so h would be 9, and your k would be 1.5. So we say this is, let's go horizontally translated 9 units to the right. Okay. And then vertically translated 1.5 units up. Sorry, up. Okay. So when breaking this down, it's pretty much what you've already done, but you need to be able to look at the equation and describe these, or be given the descriptions and make the equation. You need to be able to go both directions. I'm not going to show examples of everything. If we can go one way, we got to be able to go the other way. Okay. Now, when doing this, remember, just break down your h and k, and go off what it's telling you. So if h is positive, we're translating to the right. If h is negative, we're translating to the left. K positive up, k negative down. Now we just put units here because this problem doesn't have an actual units like feet, meters, and things like that. Okay. Now I want you guys to try one real quick, and then I'll go over it. Okay. Hopefully at this point you gave this a try. All right. And this one should have looked a little tricky, right? It's a little bit different than the ones we've done. You probably notice off the bat that you don't see an h. And I wanted to see how you guys would handle this before I told you what to do. All right. When you don't see one of those values, an h or a k, that means there's 0. When you don't see an a, that means the a is 1. Okay. So this could really be read as 1, this whole formula, 1 times w plus 0 squared minus 12. But why write all that extra stuff? Why not just write w squared if we know that w plus 0 is just whatever w is? So we don't put all of that stuff. But that means that h is 0, k is negative 12. So there's only one translation. This is vertically translated or 12 units down. Okay. Now, after kind of doing this, I think that I should show you guys one where we go the opposite direction. If I said something was horizontally translated, sorry, I was going to say shifted, but pretty close. Horizontally translated 4 units right. Actually, let's switch that to left. 4 units left. And then let's say vertically translated 2 units down. To go the opposite direction, you need to figure out what your variables would be. We know horizontally is for h. We know that vertically is for k. K is easy. 2 units down. K must be a negative 2, right? H gets a little bit tougher when you look at it the other way. 4 units to the left must mean minus 4, right? Because if we go left, it's minus. If we go right, it's positive. But when we go to plug this into the equation, f of x equals x minus h. Well, it's a negative 4, so that becomes minus whatever h is, which is negative 4, squared plus k, but k is now a negative because it's minus 2. Okay, that minus minus is going to work out to f of x equals x plus 4 squared minus 2. okay? So this is where that opposite comes in. This is the part that I always see students get confused with. It's the h value. But just remember, the original formula has a negative already in. So it's just constantly going to be switching it. All right, if h is positive, then when you plug it in, it would be a negative. If h is negative, then when you plug it in, it'll turn to a positive, okay? So I know there was a lot going on in this video, all right? And it could be a tough concept when graphing from, from the parent function, all right? I am going to get into the next lesson a little bit more about why we do it this way, okay? So I hope you guys understood it. If not, hit me with some questions in class.